So welcome back. This video is going to talk about estimating retention rates for the generalized retention model. So as a quick review, the general retention model assumes that the probability some customer fails during time t is a number r sub t. And so how do we estimate these retention probabilities, the r sub t's? The answer to that question is a class of statistical models called survival analysis. Survival analysis is a set of methods that are used to study the time until something occurs with the possibility that that event has not occurred for all of our sampling units. So the term survival analysis literally comes from the survival of a patient. So these methods were proposed for biostatistics problems where we're studying the survival of a patient. So one of the famous data sets is the leukemia data set, where we had a new treatment for leukemia, and we wanted to know if a patient receives this new treatment, does the patient survive longer than someone who doesn't get the treatment, that gets a placebo. Another famous biostatistics data set is the Stanford heart transplant data set, where we have a sample of people who received heart transplants, and we want to understand how different factors affect the survival time of those transplant recipients. These methods also get used in many other fields. So in engineering, it might be used to study the time until some part fails or some aircraft engine fails, as another example. What all of these problems have in common, whether it's the survival time of a patient or the survival time of a part or the survival time of a customer at Netflix, is that we're interested in some random variable big T indicating the time of failure. Let me just mention one more thing. Often in these CRM problems, survival analysis is used to study a positive event. So the event could be, for example, the time until repurchase. How long does it take for a customer who just bought from us to come back again? And we can use the same class of methods. Notice that censoring could also be a problem there, where we have the situation where the customer never comes back. So it's very important to account for that possibility of censoring. As we saw with the simple retention model, if we have some customer who is retained many times, we need to include that in our estimate of the retention rate. Otherwise, we get biased estimates of those retention rates. So survival analysis, I like to think of as answering three main questions. So the first question is, when is the event likely to occur? The answer to that question is going to come from either looking at an estimate of the hazard function or an estimate of the survivor function. So let me give a couple quick illustrations to show what I mean by this. So the hazard function plots h at t, the hazard function, as a function of t. Remember, the hazard function is the probability that the event occurs at time t, given that t is greater than or equal to t. And so what is very common is for this hazard function to start out high. You know, when the relationship first begins, there's a higher probability of failure, and then it decreases over time. Perhaps at some point it starts to increase again. This would be called a bathtub shaped hazard function, where this also happens with parts, where when you first install the part, there's a high probability of failure, but once it makes it past a certain point, the probability is quite low until the part wears out, and then it starts to increase again. So bathtub-shaped hazard functions are common in a lot of fields. We can also study this by looking at the survivor function. So the survivor function starts at value 1, In this case, it's going to drop very quickly, and then it's going to drop more slowly, and then drop more quickly again. So this would be a bathtub-shaped hazard function. If you think about it, the shape of the hazard function for the simple retention model, so the simple retention model has a hazard function that looks something like this. It's constant over time. The survivor function that goes along with this would look something like this. Eventually it's going to approach 0, but it's going to go down very smoothly, as opposed to the bathtub situation where it drops very quickly, then flattens out for a while, and then drops again quickly. If we have a situation where you have cancellation, so remember the cell phone example that we went over, where maybe the hazard function goes down and then it shoots up at month 6, and then it's low until month 12, and then it shoots up again, and so forth. The corresponding hazard function will go down, and then at period, it's kind of flat, and then at period 6, it drops, and then it flattens out again, it drops, flattens out again, drops, and kind of flattens out again. So this would be the survivor function when you have penalty involved and customers dropping when they're out of contract and not when they're in contract. Sometimes all we care about is the shape of the hazard function, but remember, if you know the hazard function, you can get to the survivor function and vice versa. So I just want to describe when are customers likely to churn. So that's question 1, and that's all we're going to really talk about in this lecture. Next week, we're going to have another set of videos that will treat this in more of a regression context. Question 2 is, how do static characteristics affect the probability of t occurring, or equivalently, the hazard or the survivor function? So, for example, maybe I have acquisition source. So if I acquire you through paid search versus a rented list, do you have a different shape of the survivor function? And so what could happen is the hazard function could just shift up depending on the acquisition source, or it could take on an entirely different shape. Likewise, if I have older customers versus younger customers, how does that affect things? And that's the second type of question that we're going to be able to answer once we start thinking about this in more of a regression framework. The third question is, how do things that happen during the course of the relationship affect the probability of t or the hazard of t or the survivor function? And these are called time-dependent covariates. So time-dependent covariate is a covariate that changes over time, as opposed to a static covariate, where all of these covariates don't change over time. Your acquisition source is always the same acquisition source, whereas other things do change over time. So more on that next week when we get to regression type models. So where we're going to go with this is there are non-parametric product moment estimators of these survival functions. The two main methods are the Kaplan Meier approach and the life table method. We're going to talk about those in this video. Then next week we're going to talk about some other approaches. So what are the product moment estimators? The way I like to understand these methods is to go back to this really important table that we worked on together. And let's go take a look at this particular expression. So this says the probability that you survive up until time t is just the product of the retention rates up until that point in time. If I have actual data, how do I estimate this thing? Here's the answer. So my estimate of the survival function is simply going to be the product of the retention rate. So you can think of this thing as being like my R sub t's. So R sub t is this. Well, what exactly is this? N sub t is going to be the number of customers who are at risk at time t. So at risk is the survival analysis term. The term I've been using in my discussion of the simple retention model is the number of customers who are flipping the coin at time t. So it's the number of patients still in your study, or the number of customers who are flipping the coin is the way to think about this. D sub t is the number of customers who cancel at time t. So if I take the number of cancels, divide by the number of coin flips, I have a really simple way to estimate the hazard at time t. So this ratio is just the simple estimate of the fraction of customers who cancel at time I. I've changed the index here to I, since we're going to sum I up through t. If I take 1 minus the hazard rate, I get the retention rate. So 1 minus the retention rate gives me the hazard, 1 minus the hazard gives me the retention rate. So we can think of this whole thing as being the retention rate at time I. So all I'm doing is multiplying all of my R sub i's, so notice I had the same I here, and that'll be my way of estimating the survivor function. If I know the survivor function, I can find my other functions. So here's the PMF, I can find the hazard with simply this 1 minus d sub I over n sub I. Now, what's the difference between a Kaplan Meier estimator and a life table or actuarial estimate? So the Kaplan Meier estimator, I think, is the simplest of these, and it counts all people who are censored at time t as being at risk. Life table estimates are used when you really have a continuous version of t, which we don't really have with our Netflix example, because customers are paying at discrete time points. And the life table assumes that only half of those censored at time t really are at risk. All right, so that's going to be an approach that we're not going to really use for lifetime value estimators. So let's consider a specific example. This is the example of a Japanese cram school that I actually worked with as a class project many years ago. This is a cram school targeted at junior high school kids. So in Japan, if you're in junior high school, you will go to school all day, and then your parents will probably invest in some additional education for you, because it's extremely important that you do well in junior high school so that you can get into a good high school, which means that you'll get into a good college. You'll either go to a night school where you'll do additional exercises, or you'll sign up for this service, which includes supplementary problems, so extra problem sets, and you will work through those and send them back. And at the time we had it was like a physical booklet. And this was a situation where the parents would sign up for it month by month. What I have in this table is slightly confusing. Pay close attention to this. There's a difference between customer time and calendar time. Okay, so calendar time is the calendar month that something happens. So month 1 would be January, month 2 would be February, and so forth. This is not calendar time. This is customer time. So this is how far into the relationship did this happen. Okay, so this is going to be the first month of a customer's life. So some of these customers were acquired in January, in which case month 1 would be January. If I had been acquired in April, then month 1 would be April. Okay, so this is like the clock starts when I become a customer. That is what I mean by customer time as opposed to calendar time. What this says is there are 3 customers who were censored in month 1. So what that really means is this. This is now, I have 3 customers who were acquired here, and they've been retained once. All right, so there were 3 customers who have been retained once. So the way to think about this is those 3 customers have flipped the coin exactly once. Now, I don't know what's going to happen later. So don't know what's going to happen next month. Don't know what will happen the month after. That's why they're censored. So that's what that means. This means that there were 0 customers who were acquired and canceled during their first month. So that would be a situation where, here's now, I acquired you and then you churned. So I think I was writing that as R bar or churn. Maybe I wrote it as a big C. Can't remember what exactly I wrote it as. But there were no customers in that situation. There were 3 customers like that. All right, let's do another number here. So there were 4 customers who churned in the second period. So that looks something like this. I acquired you, I retained you, and then I didn't retain you. So there were 4 customers who looked like this. They flipped the coin twice. First time it was a head, second time it was a tail, and they left. There were no customers who were censored after their second month. Let's go do 2 more. I know this is kind of tedious, but it's important to understand what's happening, and students always get confused by this. So there are 16 customers who look like this. They churned, they were retained, they were retained, they were acquired. So heads, heads, tails. So 3 coin flips ending in a tail. There were 2 customers who looked like this. They were acquired, that's an acquired, retain, retain, retained. I don't know what's going to happen next. All right, so I hope you understand what this table is describing. So in total, we had 245 customers cancel. There's 426 customers who've been acquired, and I don't know what's going to happen next. So they've not canceled yet, but they flipped the coin a whole lot of times so far. 671 total customers. Let's go work through the Kaplan Meier estimator. In period 1, I have 671 customers flipping a coin in the first month of their life as a customer. So that's the number at risk or the number of flips. What we can see is that 0 of those 671 customers decided to cancel in their first month of being a customer. So notice my estimated retention rate in period 1 is 100%. My survivor function is also 100% since you can't cancel before period 1. You pay me money and you're in period 1. Let's now go look at what happens in period 2. So there are 4 customers who cancel. 3 customers were censored after period 1. So I just acquired them last month. I don't know what's going to happen next. So notice, since I don't know what happens during this, in the second month of their life, the number of people flipping a coin in month 2 is reduced to 668. So if I take 4 divided by 668, that's going to give me the churn rate in period 2. So that retention rate is now 0.994 for period 2. How did I find my survivor function? Well, let me refresh your memory of how that worked. So what I do to get the current survival function is I take the previous retention rate times the previous survival rate. And that's exactly what I'm going to do right here. I'm going to take 1 times this number, gives me the survivor function. Well, let's keep going. 4 customers have left, and therefore I never get to see what they do in month 3 of their life. So let's reduce the number at risk, or the number of flippers, to 664. So then what is my new retention rate? It's going to be 16 divided by this. So 1 minus 16 over 664 gives me this number. Where does the survival function come from? Well, take the previous value of the survival function times the current retention rate, and I get 0.9701. And we can keep going. So where does 646 come from? Well, I had 16 cancels plus 2 censored, that's 18. If I take 664 minus those 18, I get 646. My next retention rate is going to be, take 20 divided by this, so 1 minus 20 over 646 gives me 0.969. And that gives me my newest estimate of the retention rate. Take that times the survivor function, I get the new survivor function value. And that's how I end up with my Kaplan Meier estimator. If I were to do a life table approach, I'm going to assume that only half of these are at risk. And so that's why these numbers are slightly different. Let's not worry about that for now, since it's not going to be used much with the lifetime value problems that we're estimating. So having found the survivor function, the retention rates, I can graph them. And so let's go look at them. If I look at my retention probabilities, so this would be plotting this column, the retention rates versus t, what we see is kind of an interesting graph where it looks like there's a big drop at month 7. The question is why? What's going on with month 7? The hazard function would just be 1 minus this, and so we see a big spike in churns at month 7. It's like something is happening after month 6. Now, just for contrast, I've superimposed the simple retention model estimate. So the simple retention model assumes constant hazard and retention rates over time. We can also look at the survivor function, so go plot this column against t, and we can compare that with the simple retention model estimator. So the simple retention model just decays geometrically. We're just multiplying by r sub t, which is a constant. What we can see is the survivor function is actually a bit higher when we account for this correctly, and then you get a big drop at month 7, and then it's a bit lower. The PDF or PMF, or however you want to call it, should be PMF, looks a whole lot like the hazard function, and that's because the vast majority of these customers survive through the first year. So it's really hard to tell the difference between those two. So how do we do this in R? I'm going to make a separate video that shows how to do this in Python, but for the purpose of this lecture, let's do it in R. In order to do it in R, you're going to need to install the survival package if you haven't done so already. And we can read in this data set. It's called the Service 1 Year data set. If you don't want to do that and just want to type it directly, here's how you can type it in directly. There's a function called servFit that fits these basic life table Kaplan Meier estimators. The dependent variable is going to be the time of either censoring or cancellation. So big T indicates the time of censoring or cancellation. And then this serve thing also has an indicator that indicates if the event occurred. So different software expect a different indicator in R, it's always that the event occurred. So I have a variable cancel that indicates whether or not the customer canceled. So I say some software wants to know whether or not the customer was censored, and that's slightly confusing. So I want to describe this as a function of just an intercept, if you will. We're not going to break this out by any other variable, and that's why we have a tilde1. So think of this as like the intercept model. I'm going to weight by these counts, since I have aggregated data here. I've given counts as I had in this table, so a very concise way. The alternative would be to have 671 rows in the data set, and that's probably what you'd be more likely to encounter if you were doing this with a real database for a company. But I've already done substantial aggregation to end up with these counts. If you do a summary on this fitted object, what you end up with is something that looks a lot like the table that we worked through together a couple slides ago. So we had the number at risk, we had the retention rates in the survivor function. Summary function gives us the number at risk, the number of events. So think of this as the number of flips, the number of heads. Here's your survival function. And it actually computes a standard error for us with a confidence interval. If you plot a fitted object, you get the survivor function, which looks a lot like the one that I created by hand back here. So we saw a substantial drop. Here we see a step function with a pretty substantial drop at month 7 and smaller drops for the other months. Now we could compare this with what we get with the simple retention model. So this was the formula that we had. Take the number of cancels, divide by the number of flips, subtract that from 1, and you have the retention rate. So here's my R code to do that. If I take the sum of my t-values times the counts, we end up with the number of flips. Here's the number of cancels. 1 minus that gives us the retention rate. I'd now like to work a slightly more complicated example. It turns out I had more than 1 year, but for the initial example, I wanted to keep it 1 year because it would all fit on one page. They actually gave us 5 years of data, though, when we did this project for the company. There's another data set out there called Service 5-year. And if you bring that in, what you will see is, and I can fit the same survivor function as I had before on the 5-year data. Now, if we go look at our hazard function, remember the hazard is telling me when is this event cancellation likely to occur. What we see are regular spikes at, it appears to be 7 and 13, and then another 6 months out, another 6 months out. And it's almost like there's something going on at, something after month 6 and after month 12, and every, multiple of 6 that we need to worry about. And it turns out there's another variable in the data set that we should have been accounting for, and that is the length of the initial contract. So at this company, you sign up either for a 1-month contract, so month-by-month contract, or you get a little price discount if you sign up for 6 months at a time, or if you really like them, you can sign up for a 12-month contract. And so maybe these spikes are really capturing this variable that should have been included in the analysis, which is the length of your contract. Now, before we account for that, I want to make a really important point. So here's the survivor function versus the survival function using the simple retention model. Now, when we look at the hazard function, this hazard function looks absolutely nothing like the simple retention hazard function. But when we look at the survivor function, the two look almost identical. One is a little bit above the other, then it goes a little bit below, but the two are really close to each other. And if you remember, the way we can compute lifetime value is to multiply the survival function times these m sub t's. Now, if my survival functions are roughly the same, then the lifetime values will also be roughly the same, whether I use the more complicated general retention model or if I just use the simple retention model. I think this is a kind of a profound point that the simple retention model makes a very unrealistic assumption that's probably not at all plausible in most cases. However, when it comes to computing lifetime value, it's going to come relatively close because what's happening is these retention rates are kind of averaged, and once you average them, you get something like what you have with the simple retention model. Despite the fact that we made very unrealistic assumptions, the simple retention model will get you in the ballpark, and I tend to use it very often because it's so easy to explain to people, even though it makes some pretty unrealistic assumptions. What comes out is pretty good. So the next thing I did was to compute lifetime value using the fancy generalized retention model with survival analysis estimates versus the simple retention model estimates. Now, SRM takes this out to infinity, whereas the GRM can only take it out 5 years. So to make this comparable, I've only taken the SRM out 60 months or 5 years. And so I've computed the survivor functions with both using this formula that we had here. I've computed the products of m sub t times these survival functions. I've added them up, and what we see is that using the correct general retention model, we come up with $424 as the lifetime value. With the simple retention model, we overestimate it by a little bit, but it's in the ballpark. By the way, this is assuming a period cash flow of $23.20, which was the actual amount minus some cost of goods sold, converting yen to dollars. So it was, kind of a complicated calculation. To compute this sum in R, all I do is I take the fitted survival function times, here's my m sub t's. So it's a one-liner in R to get to this number. And so again, what I'm doing is I'm just computing that same formula. Another thing that we can do is account for the fact that different customers sign up for different initial contract lengths. So this is, think of it as a static covariate. I know this at the beginning of the life of the customer. You either sign up for 1 month, 6 month, or 12-month periods. Now maybe you change that along the way, but I'm not going to account for that. That would be a time-dependent covariate. We'll deal with that next week. So the way you can break it out by some discrete covariate, if you will, is with, instead of saying tilde1, you say tilde start length. And this is going to stratify your survival analysis by this starting length. So now I end up with different survival functions depending on the length of the initial contract period. And so it's kind of interesting to compare these. The solid line shows those who were on the 1-month contracts. And what you see is that there's a fairly high hazard rate at first, but then it declines over time. So it's very common to see that declining hazard function the longer you've been a customer. The pattern for 6 month, though, is quite different. So you get a spike after 6 months, then after 12, after 18, after 24, and so forth. Whereas those on 12-month contracts tend to stay in 12-month contracts. You get a spike after 12, 24, 36, but you don't get a spike here at 6 months, 18 months, 30 months, and so forth. I think the survivor function may be even clearer, where You do a much better job of holding on to the 12-month people, and then as soon as month 12 hits, the floor drops out. Then you do a better job of holding on to them, and then the floor drops out. Whereas you get a pretty steady declining function, survivor function for the 1-monthers, and the 6 months are somewhere in between. The other thing that's very obvious from this plot is even after a long period of time, the 12-month customers are better. A higher fraction are surviving than with the 1-month contract people. We can further break this out by contract length. You can see that even with the 1-month contract length, the hazard function is not constant. You have a much higher churn probability at the beginning that declines the longer a customer has been with you, the more loyal that customer becomes. Despite that, the survivor functions are about the same, so your lifetime value estimates should be pretty similar. You could look at it for the 12s. The 12s have a radically different hazard function using the general retention model versus the simple retention model. Here the survivor functions differ a bit more. We can go compare these estimates though across them, and you can see even with this extreme 12-month case where the general and the simple retention models produce very different survival and hazard plots, the lifetime value estimates are pretty similar. So 571 versus 576. So again, the point is you can do quite well using the simple retention model, but I think you get much more understanding from looking at these hazard plots.